All right, next up will be our presenter, Martin Bureau. He is the Vice President, Innovation and PFAS lead, and his presentation is entitled The True Cost of PFAS and Why We Must Act Now. So couldn't agree more myself, Martin. So I'm really anxious to hear what you have to say, and I know our audience is as well. So go ahead and take us away.
Thank you very much. It's my pleasure to be with you today. I'm guessing the sound's good. We had an issue earlier, so you tell me if there's a problem there.
It's all good.
Great.
Doing well.
Excellent. So I'm here to talk. Sorry, I have a cold. I'm here to talk about PFAS solutions at Ultra. A word about our company. I'm going to go very fast on this. We've been around for close to 40 years, and we've dealt with complex contamination in the past. Just one statistics out of this slide, we've dealt with more than 3 billion gallons of contaminated water with hydrocarbons, dioxin and furanes, chlorinated solvents, and now PFAS. That's really our history. We did site remediation as well, but here we're focusing on water technologies. At Ultra and Senexen, we have a long history of dealing with PFAS. It actually dates back in 2001. Where we first were called for dealing with the AFFF, an aqueous film forming foam spill on a military base in Canada. And at the time, we dealt with the in-situ rinsing solution, pump and treat the appropriate hydraulic barriers to capture the contaminants, and flotation and foaming that appeared to work well for extracting that foam out of the water and then treating it with GAC. And for those who know about solutions for PFAS, that's one of the preferred solutions we can use for dealing with PFAS. Then over the years, through various incidents, some of them being very, very severe, like this disaster in 2013, we started, improving and working on those techniques to get to treat the PFAS as much as we could. And in that accident in 2013, as a matter of fact, we were faced with a massive contamination of 17 million gallons of treated water with very high AFFF concentration. And we found a lot of answers during that testing. Of course, not everything worked, but we were able to remove most of the contamination and recuperated close to 10,000 gallons of concentrated AFFF on that particular event. And that started a race for understanding what worked and what didn't work during that project. So we went with Canadian-based universities like McGill University, University of Montreal, and then we built our first pilots for performing field demonstration of PFAS remediation, which we deployed to site in 2019 and 2020, and now in 2023 we're happy to announce, after having executed several field full-scale demonstration projects at landfill sites in particular, the first water as a service contract in landfill operations for dealing with PFAS. We're very proud of that. So the question here is, what would it cost if we had to deal with a situation of PFAS contamination? I see someone has opened his mic and camera. If we had to deal with the PFAS contamination in the greater Chicago's Stickney Water Reclamation Plant. That's the second largest of its kind in the world. And that plant deals with a daily volume of 2.6 or 2.7 million cubic meter of water. That's a lot of water. Annual volume close to 1,000 billion of cubic meters of water. And if we had to deal with the type of PFAS that we can expect and reach the levels that the EPA is currently asking, and using the American Waterworks Association cost models and the EPA's cost model for dealing with PFAS in potable water, we would come to a $1.2 million a bill on a daily basis to deal with PFAS for that plant alone. Obviously, this is not sustainable. That's not something we can use, and as a result, we need two things. First, better technologies to deal with PFAS in water, and second, we need to address sources where the contamination come from to avoid having to deal with the contamination downstream at the wells, at the potable water stations, for example. So those I've used that slide before, and so I'm not going to use it today. But those sources are known. They're industrial plants that produces or uses PFAS or PFAS species. There are also landfills that passively receive those PFAS because we use it in products that find their way at end of life in landfills. There are at firefighting training area, for example, and other sites like that, which at the end ends up both in our soil, well, first in the water, through leachates, through effluents to the rivers, etc., that are not treated for PFAS, and eventually to soil and the products we consume. So our approach to PFAS is quite straightforward and very pragmatic. We've got a stream of PFAS that's of water that's highly contaminated with PFAS, and then what we do is a online continuous flow foam fractionation approach, where essentially what we try to do is taking advantage of the properties of PFAS themselves, which are surfactants or soaps for those who are less familiar with that term, and so take the advantage of that property to extract the foam that can be produced in that contaminated water as much as we can in the driest form that we can, meaning that the foam contains as little water as possible. And if you do that in a multiple reactor sequence in continuous flow, you're able to remove the driest foam possible, recirculate your water out of that foam into previous reactors, and have a very effective or efficient process for removing PFAS in water without requiring the use of media or other capture systems that at the end you'll have to get rid of and really can be avoided to some extent or to a large extent. Of course, depending on the criteria that needs to be met, and they have been getting lower and lower in terms of concentrations recently, you may require to go to a polishing step. We have our own media at Ultra, but we also use, depending on the case, surface modified absorbents, resins, or even granulated activated carbon and the like. I must say there's a whole slew of different technologies. And then that stream of treated water, will, in our case, reach non-detect levels and be considered treated and free of PFAS. Now, what do you do with the concentration stream? Well, you need to concentrate it as much as you can so that volume is reduced. That's very important. But once it's done, you go to local, it depends really on the client and what they can do with it and what the regulator will ask them to do with it. It can go to encapsulation, destruction, or other ways like a deep well injection, for example. The differentiators of our technology are numerous, but those are the most important ones. This is a PFAS treatment for which we guarantee effectiveness, provided that it falls within a definition. Of course, we can't treat everything and anything at once, but once that's well defined, we will go to as far as guaranteeing the service, the result. This is a continuous flow system. It's completely encapsulated or enclosed, if you like, which means that there's no emission, whether airborne particles, water, or VOC emissions, and that makes it a very safe, from a health and safety standpoint, equipment to use both for your employees and visitors. And that's probably the most important point. Of course, it's modular, it can be upgraded, but those are practical aspects of it. I think safety is first. We have our own in-house laboratory set up. I'm going to go very quickly on that. We have our own PFAS lab. It's very, very useful for us to optimize systems. Now I'm going to go through two field studies that we did, one in Minnesota and one in New York, just to tell you what kind of result can be obtained. This is a picture of the New York facility where we tested PFAS on a landfill site. Well, first, we went too quick here. First, a surprise. Well, it's not anymore because it tends to be always the same case. You will find that the ratio of short chain to long chain in those landfill varies very, very, very much. In that case, we had 3 times more short chain than long chain PFAS in the water, and that is definitely a challenge. Looking at results obtained over a 2-week field demonstration a pilot where we treated 90,000 gallons. We had very, very good results in terms of long chain removal efficiency straight from FF, foam fractionation. We were able to remove, in that case, 90, but often more than 99.9. But short chain PFAS, and that's what I wanted to emphasize here, really posed a challenge. We were, in that particular case, able to remove not even 50%. And that, going forward, will be a major challenge for our industry to overcome. Of course, out of the filtration using our media, we were able to go to non-detect. This should have written non-detect, not zero, but you get the idea. Now, optimizing conditions on the field can help us reduce, by using surfactants in particular, can help us reduce the amount of concentrate generated. By fine-tuning the conditions, you get to 1% of concentrate generated, and perhaps even less. We're shooting for below 1% in field testing. This is an example from Minnesota, where we mobilized to site for 6 weeks, treated close to 330,000 gallons. Again, a very different, depending of the leachate that we were provided with, you get various amount of short to long chain PFAS, which varied from let's say 50% in short chain to a large majority of short chain in the mix, which was very challenging. Now, in our optimized conditions and using, in this case, a very specific surfactant, not only were we able to remove the long chain PFAS, but also the short chain PFAS with foam fractionation alone, down to 71%, overall above 85% of removal, which is extremely important in terms of economics of process. And that, of course, led to at the exit of filtration, a removal that was almost complete, or 100% to 99.9. So our conclusion for the fields, and that's really the take-home message today, is that there are solutions to PFAS in very complex contamination. They need to be dealt with upstream so that when you end up with millions of gallons per day at a potable water plant, you don't have to deal with a diluted problem that costs a fortune to solve. But there's no such thing as a typical leachate. You need to do pilot, you need to do full-scale demonstration, and above all, a proprietary process like ours that avoids using media as much as we can or postpone its use to only reaching those non-detect levels that are needed at the end is probably the most cost-effective solution that there can be to solve the PFAS issues that we're facing in Canada and the US currently. Now, another very important conclusion is that we need to have clear targets. Landfills, industrial influence really don't know what kind of targets right now they have to deal with, and that's very important for us to answer collectively. So I'll take any questions. I know I'm a little bit off time, but that'll be a pleasure. Thank you.
Great job. A lot of good information there, very pertinent. It's very close to home, especially where right here at Water Online headquarters is in a town outside of Philadelphia when this township had recently gone through having to deal with high levels of PFAS. And they actually they handled it efficiently, correctly, and quickly. And we're happy to report that it's under control. But it is a pertinent issue for a lot of municipalities out there. One of the things that popped up recently pertinent to what you were talking about there is, and the question that I do have for you is that are EPA's upper limits that are currently being considered for potable water really achievable? I mean, especially in the case of like a high concentration of fluids like leachates.
Well, that's a question that is well, first of all, a great question. It's difficult to answer in the sense that we don't know whether those limits will be applied to effluents like those. Definitely, we need to know if the limits that are targeted today for nanograms per liter for PFOA and PFOS, for example, right now, how will that be translated to effluents? But they are achievable. Now, the message here is that instead of trying to reach potable water levels in those effluents, let's deal with 99.9% of that contamination. We've seen sites where, the flow is not that high. It's 1,000 gallons, 100,000 gallons a day tops. Typically, not more than that. But the concentration is 1 ppm, 1 million times those targets of the EPA. So imagine it's like having 1 million times a plant that produces 100,000 gallons a day. It's huge. That can be easily done very cost effectively for a few cents a gallon. Not 10, 20, $1 a gallon like destruction techniques will show you. A few cents, depends on the case. I won't give you a specific, value. But so the answer is yes, but it might not be necessary to do that, but do that in the most pragmatic and cost-effective way for sure.
Excellent. Well, Martin, I appreciate you bringing this timely presentation to the table and to our audience. Very well done. A lot of good information out there. Looking forward to having you back. Martin, thank you very much.
My pleasure. Thank you.